In this lesson, we're going to learn how to find the average rate between 2 points on a curve. To begin talking about this, let me draw on some curve and some graph. So to be clear, in this lesson, we'd like to find the average slope across two endpoints on this graph. So let me go ahead and draw on the two endpoints. Now, so much of the study of calculus is going to be interested in finding exact gradients at particular points. But in this lesson, we're not interested in that. I want you to understand that sometimes we just want the average rate between these 2 points over here. So I'll just give you an example just to make this clear. Imagine the y value was the amount of money in your bank account, and imagine the x value was the time. If you were dealing with money, you just look at the change in the amount of money as the amount of profit or loss you'd made in that day. Now, whilst you wouldn't be so interested in the instantaneous amount of profit you made at a particular time, I think you would be a little bit more interested in the average profit you made over a number of different days. So I think a very natural question that a lot of business owners would like to answer is how much profit have they made over a really large interval in time? In fact, if you actually think of this curve to represent the amount of money in your bank account, I think most of what I say in this video isn't actually going to be super surprising to you. Now, just by looking at the slope between A and B, you can see that the slope is constantly changing at every single x value. But there's actually a really cool trick to help us find the average slope between A and B. In order to illustrate the point properly, let me go ahead and break this curve up into many smaller intervals. So what we'd like to do in this lesson is to find the average of all of these different slopes. To actually begin doing this, we have to label the x values. So let's label this first x value A as x1, and then the second one can be x2, then x3, then x4. The ellipses over here indicate that we can have as many intervals as we like, and then this final interval over here can be called xn, and then this one would be xn minus 1. Now, in order to find the average slope, let's also label the slopes. This slope can be m1, this can be m2, this can be m3, and then so on. Now, to find the average gradient, we just need to add up all the gradients and then divide by n, since there are n gradients. Now, the bar over the top of the m over here indicates that we're finding the mean, or the average. Now, calculating this average in the general case is actually needlessly complicated. So instead, I'm going to go ahead and show you a specific example that'll get the basic idea across. Let's pretend that a was equal to 1 and that b was 4, and we broke the length between them into 3 subintervals. Now in this case, the average gradient is just m1 plus m2 plus m3 divided by 3. Now to evaluate this, let me go ahead and bring the 3 out the front. Now to begin, we're going to try to find the gradient of the interval m1 by drawing a triangle underneath it. Now keep in mind that the coordinate of this point is just 1 f of 1, and the coordinate of this point is just 2 f of 2. And therefore, the height of the triangle is just going to be f of 2 minus f of 1, just like it always is. And the width of the triangle is just going to be 1/3 of the total width between 1 and 4. However, just to illustrate a point, instead of writing w on 3, I'll just write this as change in x for now. And therefore, we can write m1 as f2 minus f1 divided by change in x. And now we could repeat the exact same process for m2 and m3. m2 would just be f of 3 minus f of 2 divided by change in x. And then m3 would just be f of 4 minus f of 3 divided by the same change in x. Okay, so now we can go ahead and simplify things a little bit. You can see that all of them have a change in x in the bottom, so I'm going to rip it out of the denominator. Now that we've simplified the equation like this, something really strange happens. Notice that the f of 2's just cross out, and the f of 3's also just cross out. And if we look at the denominator, we notice that 3 times change in x is just the exact same thing as the width, so we can replace that as well. Now I also just want you to note, it doesn't actually matter how many subintervals we have. We could have had 10 or 20, and you'd still get w on the bottom. And also, everything except the last term and the first term would just end up crossing out. Now we can just bring the f of 4 minus f of 1 to the numerator, and we can say that w is just the same thing as 4 minus 1. Now it looks like we just rearranged an equation, and that's great and all, but actually something really interesting has happened, which I can go ahead and show you by copying over the graph. Now in this equation, we know that 4 is b and 1 is just a, so let's replace that. Now if we actually look at the graph on the right, we can actually draw a line directly from a to b. Now if we just go ahead and draw a triangle beneath this line, we can find its gradient as well. Now the width of this triangle is just b minus a. And the height of this triangle is just f of b minus f of a. Now, if we were to actually go ahead and divide the rise by the run of this triangle, I just want you to notice that it's exactly the same as this equation over here. And this immediately tells us that the average gradient is the same as the gradient of this line over here. Now the interesting thing about this is that it didn't actually matter how many intervals we broke this up into. So that means, regardless of how many subintervals we have, this is always going to be true. And therefore, we've actually found another way to write the average gradient. So let's write this in the general form as well. So in our simple example, we found that the slope of this line was equal to the slope of the average gradient. If we draw a faint triangle above this line, then we know its width is just b minus a. And its height can be written as f of b minus f of a. And therefore we can say that the rise over the run is just f of b minus f of a divided by b minus a. So at least for me, this is actually a really cool and quite unexpected result. It's telling us that no matter what shape you have connecting A and B, as long as we start at this point and end at this point, the average slope is going to be f of b minus f of a divided by b minus a. Now it's also possible to write this interval as the total change in x, and this interval as the total change in y. And therefore we can say that between any two endpoints, the average gradient is just going to be the change in y divided by the change in x of those two endpoints. Now this equation over here is actually the general working principle of an average speed camera. So let me just show you exactly how it's used. Now none of this is actually drawn to scale, but it is meant to illustrate a point. Let's imagine that the driver of this car decided to speed throughout this whole highway, but decided to slow down just before the checkpoints. If we draw a graph of the driver's position as a function of time, we've got the positions of the cameras over here, and we've got the distance in kilometers between them. We're going to record the position of the car in terms of time. Now, as we can see, the driver of this car was being nice and well behaved in front of the cameras. But as we can see, in the open road, they completely raced to the other side. However, whenever there's a pair of cameras like this, we can say that the average speed can be found between them. Now, assuming that the speed limit on this road was 100 kilometers an hour, then we'd actually like to find out whether this driver was exceeding the speed limit. Now it turns out that if the average gradient was higher than the speed limit, then the driver was definitely speeding. This is because for any average, whenever you have an average, there have to be numbers bigger than and smaller than the average as well. To actually find the average speed, we just draw a triangle beneath this average slope. Now it looks like in this time the driver has covered approximately 250 kilometers. And from the time they hit the first checkpoint, it looks like approximately 1 hour and 45 minutes has elapsed. And therefore, the average speed of the driver is just 250 kilometers divided by 1.75 hours. Now we can just check what 250 divided by 1.75 is in our calculator to find their average speed. So we notice that the speed of this driver is approximately 143 kilometers per hour. And therefore I think it's pretty safe to say that the driver is in a little bit of trouble. And now we've actually completed our example. And now we'll just summarize the lesson. We found that the average gradient between points A and B can be found by adding all of the individual gradients and dividing by the number of intervals. However, in a really strange and quite remarkable result, we found that this is the exact same as f of b minus f of a divided by b minus a. And therefore, for any curve, no matter what shape, we can find the average gradient just by finding the rise over the run. And this actually completes our discussion on average rates.